Welcome to NARI SimCenter's Live Expert Tips, where we cover diverse aspects of simulation and modeling in natural hazards engineering. Each session includes a technical example that demonstrates a feature of SimCenter tools relevant to research in natural hazards and their effects on the built environment. In today's session, we introduce you to hurricane risk assessment at a building level resolution using SimCenter's Pelicun framework. In today's session, Dr. Zsarnóczay will demonstrate this through an example simulating Hurricane Laura's impact on Lake Charles, Louisiana. Dr. Zsarnóczay is a research engineer at the John A. Bloom Earthquake Engineering Center at Stanford University, where his work focuses on disaster simulations that support multi-hazard risk assessment and management at a regional scale. At the SimCenter, Adam is the Associate Director for Research Outreach. He completed his PhD in civil engineering at the Budapest University of Technology and Economics, where he was also an assistant professor. He has research experience working at scales that range from individual structural members through a building up to cities with hundreds of thousands of assets. His research interests include probabilistic natural hazard assessment, model development and calibration for structural response estimation and performance assessment, and uncertainty quantification in large-scale regional simulations. Adam, thank you for being here, and you're welcome to begin.
Thank you very much, Ben. Welcome, everyone. I'm really happy to see a lot of people in the audience, a lot of familiar names, and I hope you will find this live expert tip or the few tips that I give you helpful. I'm planning a shorter session than last time. This is the second time I'm talking about Pelicun. If you haven't seen the last one and you are interested in FEMA P58, I recommend you to check it. There's a link on our website to the recording. So this is going to be a little bit shorter, and I hope we will have more time for discussion about the kind of possibilities that you see through these new features in Pelicun, and perhaps some feature requests that you can share with me, because this version of Pelicun, this is Pelicun 3, is still in beta, so it's still possible to make even bigger changes to it if there are good ideas in the community on what else would be helpful or useful for you. So let's jump into it. For those who have not been to a SimCenter event before, or who has no understanding of what we are doing, I prepared two quick slides. So those who have already seen this, please don't get scared. It's not going to take a lot of time, but I want to introduce what we are doing for the newcomers as well. So SimCenter's mandate is to support computational simulation in the natural hazards engineering community. And as part of that, we are building a framework around the performance-based engineering idea or paradigm that was created at the Peer Center at Berkeley. And since then, it's been used at many research centers and in the industry as well. We take this idea of marching from information about a facility and some hazard information through successive steps until we get results about the losses or the risk in an area. We perform structural analysis, estimate the damages, and then based on the damages, we use consequence models to estimate the losses. Most of the things we create are not new, but we are looking for models and methods in the community. And the main contribution of the center is integrating these methods into an application framework. It works much like the puzzle pieces that you see below, where you can pick and choose the applications that you like, and then we make sure that they work together and seamlessly transfer data from the inputs all the way to the outputs of your analysis. Everything we create is open source. We support multiple types of hazards, and we strive to provide multiple levels of fidelity so that you can choose the type of modeling and the type of resolution that your data supports and your research needs. This is it in a nutshell. Specifically, the performance assessment part that we are going to talk about today, that is related to Pelicun, is covered by Pelicun in the SimCenter. Pelicun is integrating damage and loss assessment methods and different ideas in this smaller puzzle piece, just like the SimCenter is integrating models and methods on a bigger scale. Today, we are going to talk about wind hazard and wind risk or wind-related risk, but Pelicun is also capable of calculating losses and damages for other types of hazards. Currently, we have earthquake and water fragility and consequence functions included in Pelicun, and it is easily extendable to other areas if there are supporting data available. That was the introduction. So from now on comes the content of the live expert tips for today. This is the flyer that we sent out, and I am going to use that to explain the main topics that we are going to touch on today. So the main idea today that we are going to look at is building level wind damage and loss assessment using Pelicun. As you can see, this green area is covering the damage and loss part. So we are not going to talk about how the wind speeds are calculated, and we are also not going to talk about how a building information can be collected about an area. We are going to mention the type of damage and loss models that are used in Hazus and contrast them with the ones that are used in Pelicun. I believe the SimCenter made some important enhancements over the Hazus models without changing the outcomes or the data itself. And this is, I believe you would be interested in these changes or these upgrades. And then we will also talk about how to enhance the data that might be available in a region with additional features or additional understanding of certain building features that you cannot really collect or infer from, say, satellite images or street view images, regardless of how sophisticated of a machine learning method you have. So we will talk about Rulesets that were also developed by people at the SimCenter and apply them in this example. These are the two intermediate pieces. And then when it comes to the entire workflow, we will look at how to run such a damage and loss assessment for a single building with different types of uncertainties considered. That's why we have the uncertainty quantification at the bottom of the slide. And then after we understood how it works for a single building, we will scale it up to a regional assessment using data from Lake Charles, Louisiana, from a hindcast that we did for Hurricane Laura that happened almost 2 years ago. So this is the plan. Let's start with the risk assessment in Hazus and comparing that with how the risk assessment happens in Pelicun or in the SimCenter tools. The main problem, in my opinion, with the risk assessment in the Hazus technical manual and in the Hazus methodology is that the damage analysis is decoupled from the loss analysis. So instead of the serial progress that we see here in the flyer that we sent out, and that is typical in the performance-based engineering framework, what happens in Hazus is that they have a separate damage calculation and a loss calculation. Losses are controlled by a single function. You see 4 functions here, but they correspond to different terrain roughnesses. So if you have a specific terrain roughness, then given the wind speed, you can always obtain a single loss ratio for a building. Notice also that there is no uncertainty about the losses. So if you know the wind speed, the losses are deterministic. When it comes to the damages, given the wind speed, you can obtain information about the likelihood of different damage states as an outcome of this particular wind speed on the building. But from these damage states, you don't move on to anything else. So you would have these damage states available, but they might be in disagreement with the losses that you get. For example, you can imagine that in this particular case, at 130 miles an hour, you have a probability, not a really large likelihood, but you have the probability of getting no damage. And even though you had no damage, you could read a particular loss value. And that value would be the same even if you arrive at a different damage state. So the wind speed gives you a loss value that is not really changing depending on what damage state the building is in. And that probably stems from the intended application of this framework. So this is not necessarily a mistake. I would rather say that by coupling these two, I think we can do more with the framework than what it was just originally intended for. Another smaller issue is that all of these curves are piecewise linear. It is not easy to see that, but there's one data point at every 5 miles an hour, and they are connected linearly. This is making the calculations a little, no, it's actually quite a bit less efficient, because you always have to interpolate between the points and then calculate the results, rather than having a log normal function where you can just get the value from the function in a single command or in a single calculation. So what we did, this already kind of suggests what we did. First, what we did is we looked at these functions, extracted the data from the Hazus database that is available publicly. And starting with the damage side, we fit log normal or normal cumulative distribution functions to the data. The choice between log normal and normal was dictated by which one provided a better fit. And having these 4 functions fit to the data, we could look at what loss ratios should we use to obtain the same loss distribution that corresponded to the same building in the Hazus database. So we coupled the two things, the damages and the losses, because they came from a numerical simulation. And it made sense that they should have some kind of a relationship that is probably not too complicated. And what we found is that in the vast majority of the cases, I would say definitely about 97% of the cases, there is a really clean connection. And by using deterministic losses, so for a given damage state, we assign a particular loss ratio, we get this expected loss curve back almost perfectly. So we are able to store the information in a much smaller space because we don't need to store every single point. We only need to store the 2 parameters of each function. And we are able to do more efficient calculations. And more importantly, we are able to review these functions now, compare them, because each function can be summarized by 2 data points. We could see, for example, all the different archetypes that are defined in the wind technical manual in Hazus, which is around 20,000 different archetypes. We could compare their parameters and decide which one is the most important, which one is more influential on the damages and on the loss ratios that are assigned to them. So I think there's a lot of potential in such data. And because of that, we found it also very important to share it with everyone. And this data is available online in a CSV file, actually in 2 CSV files. One file contains the fragility functions. You can see this is the structure of it. It has a hierarchical header. And for each damage state, or what I call limit state in Pelicun, you can see the 2 parameters of the normal or log normal functions. It's very straightforward. There are 4 functions. There are 8 parameters. And then it also provides information about the demand and the unit of the demand, which of course controls these values, these parameters in the functions. So this is available. And then given the damage states, another file contains the loss ratios. So again, for every single archetype in the Hazus database or in the Hazus methodology, you have a specific loss ratio identified that you can use, you can look at if it helps your research. To learn more about what each of these identifiers mean or what kind of archetype they describe, there is a JSON file included with these, which provides the metadata that explains what each of those codes mean. So I hope you will find that helpful. This is part of Pelicun, and I will also include it on DesignSafe. All of the examples that I share here, including last like 3 months ago, the live expert tips and today's live expert tip with the Jupyter notebook, is shared on a project in DesignSafe, and I will include a link at the end of the presentation to that project. So you can go there, look at the files, and use them if you are interested. Today's files will be there in about an hour after the presentation. So, oh, and another important thing, yes, because there are 20,000 of these, when you are looking for a particular building, or you want to do analysis and you just want to see what kind of archetypes are there, it would be quite helpful, we thought, if you could look at the functions, and you could also look at the metadata that is provided in the JSON file, and you could look at the available archetypes. So we are preparing an application that will run both on your desktop and on the web, depending on which one you prefer. And you can load these databases that are available in that application and review all the functions, choose the ones that you would like to use, and then prepare them in a format that will be compatible with all of our applications, including Pelicun. Besides the hurricane functions, we also have the entire earthquake damage and loss database from Hazus available in a similar format, and the FEMA P58 damage and loss database available like this. Okay, so with this introduction now, after this introduction, I would like to go and look at a couple of examples. So for the first example, we are looking at something very simple. It will be a single building subjected to constant wind or deterministic wind speed. There is no uncertainty about the wind speed, and we will review how to do that kind of a calculation in Pelicun. Now, if you look at the archetype here that I chose, you can see that this is a quite sophisticated description and specific description of a particular building. It's a wooden building, single family, and there are a couple of other parameters. This will be important as we move to the regional scope, because it's, as you probably know, if you've tried doing regional analysis, it's pretty difficult to understand and identify all of these parameters for a building. And this is where Rulesets will be important when we return to the presentation. But first, let me jump to my Jupyter notebook. So this notebook is the one that I will share on DesignSafe. You can see that there are 4 steps in today's live expert tips. We will start with this single building example that is described in more detail. Then we will make it more complex in 2 steps. And then we will finish with a portfolio assessment. So starting with the example, and this is just for those who have not seen the presentation and only look at the Jupyter notebook, we will need to set up an environment. These, I will uncomment them when you are on Jupyter. They install the different packages that are used in the example. And then the calculation starts with initializing a Pelicun assessment. This assessment is imported from Pelicun here. Okay, so you start an assessment, and then there are 4 steps: demands, asset information, damage calculation, and loss ratios calculation. As I mentioned, the first example is very simple, intentionally to show you the basic steps that are required every time. So the wind speed is going to be constant. We are loading a single constant wind speed value into Pelicun, and then we generate a sample based on that single value. That sample will be 1,000 identical wind speed values for a Monte Carlo analysis. So we will propagate these 1,000 values through our analysis. That 1,000 is set up here. So if you want to test a different sample size, you can change it, and you can see how that affects the analysis. The size of the sample does not influence the runtime significantly. So if you are interested in bigger sizes, you can go up to like 100,000 without really impacting how long it takes to run. The runtime is most affected by the number of buildings, not the size of the sample. So once we have this set up, you can see that Pelicun has this logging functionality, so you can see what is happening. And then we can see in this statistical description of the samples that I obtained through this function here that Pelicun indeed generated 1,000 samples, and they are all identical, 150 miles an hour. Okay, now we move on to identifying the asset itself. The asset is going to be a single component in this analysis, just like it is in Hazus. The single component is identified by the archetype description, which is this long description here. And everything else that, if you look at the previous example in FEMA P58, these are much more complicated things. Here, what we say is that we have a component in location 1 pointing in direction 1 because there's only a single building, and there is no uncertainty about the number or the quantity of this component. So everything is 1. And then this is how it looks like when it's generated. It's a data frame. Pelicun works with data frames. It can work with files as well, but when you are in a Jupyter environment, it is much easier to just create a data frame like this and then feed it into Pelicun by using the load model function of the asset or the demand, or even the damage could be loaded if you prefer to start with damage. So we load the component model and then generate a sample based on this model, which is again going to be very simple. It's one component for all 1,000 analysis, as you can see down here. Okay, so far it's quite straightforward, I believe. And then we are not using any custom models. You could do that. So you could take this fragility database that I mentioned that is in the CSV file, open it in Excel, and then change any of the fragility parameters and load it into Pelicun just like this, instead of using the Pelicun default keyword here, which is a special starting folder that Pelicun understands and replaces with the path to its own database. You could use an actual path on your computer to a CSV file where you have your own fragility functions. And if they are defined in the same format that I just shown earlier, Pelicun will understand them and use them and look for this component in that database. So in our case, we use the default one, and then here calculate the damages simply by saying damage calculate and providing a sample size. And everything else is just about plotting what we found. You can see that we have 4 different damage states for this single component in location 1. And this is the probability of the building being in each of the damage states. The labels here are shifted. So this is damage state 1, this is 2, 3, and 4. This is the same data that you can see up here. So you see that there's about 45% chance of damage state 2, basically. And then there's a very little chance of damage state 4 based on these results. Okay, this was very simple. You could even do this in the back of the envelope because you look at the fragilities and you read the portions of the areas between the consecutive curves and find the probability of damage states. Now we will use the loss calculation to assign losses to each of these damage states and then get an idea about the expected losses for this component. Loss calculations in Pelicun are separated from damage calculations to allow you to link different damage descriptions or fragility function sets to different consequence functions. In our case, we are not going to do anything like that, so we use the corresponding consequence functions from Hazus for the damage calculation and have a very simple mapping here. But you could separate these things and say that you come up with a new consequence function, a new loss function, for example, that is not deterministic. You could say that it has some uncertainty around the median value, and then link that to the original Hazus damage function in this step if you are interested in doing something like that. And you could do this for every single archetype in the database. So we start with this mapping, and then using the map that we defined, we load the default loss or consequence database and calculate the losses, again, with a single line of code. And what we see is how the different consequence functions are defined here. So for each damage state, we can see the actual losses that were loaded. And then for each damage state, here we can see the average loss that was calculated and the likelihood of different loss ratios. Again, you have 4 bars because you have 4 possible damage states, and each damage state has a deterministic loss value associated with it in this case. Okay, so this was the simple example. Now we will make it a little more complicated by introducing uncertainty in the demand. So rather than using a single deterministic wind speed that was 150 miles an hour, now we will use wind speed with a log normal distribution with a median of 150 miles an hour, but we put a 0.2 log standard deviation on it. And what I would like you to notice here is that we don't have to restart the entire analysis and redefine everything. All we have to do is change the demand part of the calculation. So we will update our input demand here with the data frame again. If you look at it, it will look like this. It identifies the location of the demand. We have only one building, so this is going to be peak wind speed, that's PWS. And then 1 means it's location 1, direction 1, and units, the type of distribution, the first parameter, and the second parameter of the distribution. That's all we need. Once we have this data frame, we can feed it into the demand part of the assessment by loading it in, and then regenerate the demand samples. And as you can see below, now we have a distribution that goes from 77 to 289. That's a pretty large number, but with 1,000 samples and such a log normal distribution, that is even possible. You could include truncation here. So you could say that there is an upper limit to the wind speed that I want to simulate, and Pelicun would be able to handle that. So once we have this demand, we do not need to redefine the damage model, redefine the components. We can immediately say, I would like to recalculate the damage, and I would like to recalculate the losses, and that's it. And Pelicun takes care of the calculations and presents you the damages and then the losses. And now you can see that we have a little more options in the loss values, actually 1 more, because now we have the option of no damage, and then damage state 1, 2, 3, 4. Each has its own corresponding loss ratio. You can also see, if you compare these bar charts, let's pick one value. Let's take damage state 1 has a 26% probability. If we go back to the previous case, its probability was 33%. So by including uncertainty in the demand, of course, we are changing the likelihood of different damage states in the result. Okay, now the third step is adding more complexity by recognizing that we cannot be certain about the type of archetype that is best fitting our building. If you think about a regional assessment, oftentimes you don't know enough about the buildings to zero in on a particular archetype. You would rather be able to say it's one of a few options. Even if you know the building very well, it is possible that it's not matching any of the exact archetypes that are provided in Hazus, and you would like to include multiple options and see how the average of those describes the performance of the building. So in this case, what I did is, for the sake of simplicity, I picked the terrain as the uncertainty, this is the terrain roughness that is included in the description of the archetype, which describes how dense are the surroundings of the building, and because this kind of density affects the wind speeds and the wind characteristics that in turn affect how damaging that wind is going to be on the building. The smaller this number is, the more open the terrain is around the building. So we look at 5 different roughness values. These are the 5 values that are used in Hazus, and then assign probabilities to each of them. This is a categorical distribution essentially. And then what we will do is we would like to consider all 5 archetypes from Hazus and perform an analysis. This is still a single building analysis, but perform it with each different archetype and then see how the choice of the archetype affects the losses, and then combine those results to get an expected loss for all of these possibilities. What we do, again, we will need to create a data frame here. This data frame will have the 5 different archetypes included, and then it will each realization. So in the horizontal axis, now you see realizations, they go from 0 to 999. I'm only plotting a part of them. So in each realization of the component, we are choosing one archetype. We are choosing this middle one for the first one, this one for the second one, this one for the third one, and so on. And these choices follow the distribution that we had set up and defined here. So as you can see here, where I summed up the ones in each row here, the most likely is this one with the 70, and the least likely is this one with the 3. So we created a component sample that describes the uncertainty we have in the component descriptions. And this is a very powerful thing that was not available in Pelicun 2. This allows you, both at the building level and at the regional level, to have any kind of uncertainties in the components considered in the analysis. You can have completely different sets of components defined for the same analysis, but half of the sample works with one type of the component configuration and the other half of the sample will work with the other. This allows you to consider even correlations between component quantities in a more complex analysis where you have more than one component. But in this particular case, it's one or the other. So it's exclusive, either this one or this one or this one or this one or the other one. None of the cases, none of the realizations have 2 components simultaneously available in the building. Okay, everything is set up here for this. And then at this step, we are loading the sample into the calculation, and we need to make small adjustments to the damage and the losses in this case, because what Pelicun does when it loads the damage model from the database, it only loads the parts that have active components corresponding to it. So if I only have one component defined and I load the damage database, it will only pull one row from the database. So I have to reload the database. And then Pelicun recognizes that there are 5 different components, and I show you here all the data that is loaded for them. So you can see how, for example, the median of the fragility curves changes as you change the terrain roughness for this particular component. You can see the different values. The changes are not huge, but there are other parameters in the components where the changes could be much more substantial. So there are these 5 options loaded into the damage calculation, and then we calculate the damages. Also notice that this takes about 1 second. So we are still looking at only a single building, of course, but it is very fast. And then we can review the results first in a very detailed form, where you can see every single archetype separately and the damage state for each archetype in each realization separately. So this allows you the highest level of granularity that is possible. And then, of course, you can aggregate across archetypes, you can aggregate across damage states. It allows you to filter the data according to your research needs. And then given this damage information, we can move on to the loss assessment and calculate loss ratios. Again, we need a mapping similar to previously. We take the name of the archetype for the damage and use it the same name for the losses, because we have these coupled models in Hazus that we created, as I showed at the beginning of the presentation. Once we have this mapping available, Similarly to the damage case, we have to reload the consequence models because Pelicun filters them according to the components that are identified here. And you can see that now we have 5 different models identified with 5 different loss ratios for each damage state. All of these will be used in the loss assessment to get losses for each type of archetype, and then we can aggregate them. And here you can see the loss ratios. Now you can see that through the extra uncertainty in the archetypes, we are introducing even more options, both in terms of losses and in the likelihood of those losses happening. So out of the 1,000 cases, you can see that there's now actually a quite significant number that leads to complete loss, just because we have this uncertainty in the components, in the archetypes, and in the demand. So before moving to the building portfolio, let me jump back to the presentation because there is an important detail that I would like to cover. And this is Rulesets. When it comes to a portfolio of buildings in a regional assessment, there are, as you saw, these archetypes are pretty specific. There are a lot of details that you would need to know. And of course, you could use the methods that I just shown to introduce uncertainty about those details and then start considering more and more archetypes for a single building. But ideally, you would try to reduce that uncertainty as much as you can. So if you have some information about the local building codes or about the local design trends or about some other details of how the local population complies with the rules, with the designs, with the mandates in the area, you can use them and automatically select or populate certain parts of these required attribute tables for the buildings in the area. And this is what we did in our testbed for Lake Charles. This effort was led by Professor Tracy Kijewski-Correa, and I also link to the documentation of that testbed in the Jupyter notebook, as you will see. So if you're interested in the development of these rule sets, you can learn more about it in that documentation. But the way they work, I will show it right now, and it is part of the Jupyter notebook here. We have tables where we march in time from the earliest standards available in the area until today. And for each era, for each design era, we identify how the design was performed in a typical firm, considering those details that are required by Hazus. So in this case, for example, depending on the roof shape, we assign a type of secondary water resistance. And we look at every single attribute that is required by Hazus and try to assign something. If we cannot, then we might do something that involves a random variable and some uncertainty. And then everything from these tables is translated into Python scripts. And these Python scripts are available on GitHub. So you can download them. And if you have a project in Louisiana, you can use them to infer details of buildings. If you have a project in another state, you can use them, but you should be careful because the rules and the standards and the compliance could be very different between the states in the eastern part of the United States. So let's see how this applies to a regional assessment. Here are the links to the work we did, the documentation of it, and then the data that is published from that documentation related to the rule sets and the building inventory and the hazard simulation, and also the results of that regional simulation. We're going to do a simplified version of that here for the sake of brevity. It is possible to do the entire calculation within this Jupyter notebook because it uses the same damage and loss functions and building inventory that we used in the testbed. So I'm loading the building inventory here. You can see the first 5 buildings, and this gives you an idea about the kinds of attributes that are available for those buildings. Some of these attributes were collected through machine learning techniques using computer vision. So not all of them are available just off the shelf for a regional assessment. And as you can see, if you review these attributes, these are still not enough to recognize or to identify the kind of archetype that corresponds to this particular building. You can see it's hipped roof at 1962. It was built in 1962. You have an idea about the roof slope, the height of the roof, the number of stories. So this is not bad, but you don't know, for example, the nail spacing on the roof, which is required to understand or to identify the archetype in Hazus. You don't know if it has shutters or not. So to do this, I use the rule sets and this function. I just need to find it. This function, yes, the autopopulate function here. This function, I will jump up just for a second for you to see. So we are down here now in the assets building inventory part. I will jump up to the beginning. This function was imported here. So this is part of the lake charts rule sets. It will be included in the project that I share, that Pelicun project, and you will be able to import it just like I did. So there is this autopopulate function, which I provide a BIM file. The BIM file stands for Building Information Model file, and it includes this information for a particular building. So I provide that BIM file, and it returns an extended version of that BIM file with additional features and parameters. And more importantly, it returns the archetype that it identified for it. So here I assumed that we are not sure about the year built and put a normal distribution on it with a 10-year standard deviation. So rather than saying the building was built in 1962, I say that it's somewhere between 1940 and 1975, maybe 1980. And then I generate the 1,000 samples that I use for the Monte Carlo analysis in this example with a different year for every sample, for every building. And then given the different year, through autopopulation, I always land in a different standard era, different design era, and I get maybe a different archetype for the building. So this way, I have the kind of uncertainty and archetype assignment that we saw in the third step, but now we brought it to the regional level, and we can do it for every single building in the assessment. I only ran 100 buildings here so that you can repeat it in a short time. This runs in about 20 seconds. It scales roughly linearly with buildings up to a certain point. So you should be able to run about 10,000 buildings with it without any problems. And that would take about 2,000 seconds, so less than an hour on your local computer. So this doesn't need a supercomputer or anything like that. So you can see that after picking 100 buildings, we found 414 different archetypes. And each of them is assigned to a certain realization. These are the realizations. So you can think about it as different versions of the city that we are looking at. Goes from 0 to 1,000 because we are looking at 1,000 different options. And in each option, for each location, the location is the building that we are looking at. So we are looking at 100 buildings. It goes from 0 to 99. So for each building, we have only one option, right? First building has 4 possibilities, one here, one. You see that it's always one option in one realization. That's the idea behind this technique. And then other than this, everything stays the same. So we prepared this matrix, and it only takes this much to prepare it. And then we create we add units to the component sample. That's not that important. In this case, the units are always each because you are looking at a building level assessment. Feed the sample to the analysis and define intensity measures. So for each building now of the 100, you need to have a wind speed available. Here, what I do is I take the wind speed that was estimated by ARA for the area, based on their own wind simulations, which is 102 miles an hour for Hurricane Laura. I put a 10% standard deviation on it, just to have some uncertainty about the wind speed considered. And then I assign a random value to each building that I'm looking at, so each of the 100 buildings. And I load those demands, sample them, and I show the sample down here. So you can see that for each of the 100 locations, I have the same mean because I assigned the same wind speed, but a different realization for every single case. So there is some uncertainty in the wind field in the area. And then I reload the damage model like we did before and recalculate the damages. You can see that it took 21 seconds for 100 buildings. And you can see this is the result. So for each building type, for each location, you see the possible damage states. So you can separate damages and look at them by buildings. You can look at them by different archetypes. You can say, I want to see if the buildings have shutters. Do they experience more damage than without shutters? So you can separate the archetypes like that and see, compare by damage state, for example, if that's what you're interested in. Or you can just take these damages and move on, look at the losses. And then when it comes to losses, we need a mapping again. This is the straightforward mapping again that we did before in the previous steps. And then calculate the losses, load the database, run the calculation with this line, and then we can look at detailed losses, which are oftentimes more difficult to capture, or you can aggregate them. Here I aggregated them around those 100 buildings, and you can see that on aggregate, your expected loss is 2.3 building values in the city, which for such a low wind speed might be more than what you would expect. And the median value is also 2.1. It can go up to 6 or go down to 0.4. So this is over 1,000 analysis, over 100 buildings in the Lake Charles area. Now, in the interest of time, I jump back here and show you a few resources that you will hopefully find helpful. I will have this as a shared project on DesignSafe. This project already exists. So if you remember this number, that's the only thing you have to remember, 3411. If you remember this number, you can find the project on DesignSafe. You can see the previous live expert tip shared there, and you will see this shared in an hour or 2 hours in this afternoon. And you can download the Jupyter notebook. You can download this presentation and all the supporting data. You will also see some maps in the Jupyter notebook where I show you the damages and the losses for the area. And then the SimCenter website, the GitHub place for Pelicun, and the documentation of Pelicun are also helpful resources. And before I stop, I want to mention that all of these great people helped putting that Lake Charles testbed together. So that is not my only, or not my work alone. It is a work of a big team, and I am only the one who is presenting it to you. Thank you for your attention. Even though I planned to do this short, it happened to become longer than I expected, but I hope you will still have questions and you stay for the next few minutes to ask them. Thank you.
Adam, thank you very much for that informative presentation. I want to remind attendees that you can sign up for or register for upcoming live expert tips at our webpage, which is simcenter.designsafe-ci.org. This concludes today's live expert tips with the NERI SimCenter. We hope you've been inspired to pick up this example that Adam has covered and adapt the capabilities to your present research. Again, Adam, thank you very much for this presentation.